Esters are one of the most important carboxylic acid derivatives that we're going to talk about. They're found throughout biology, and we're going to talk about a lot of the interesting examples of esters, biologically relevant esters like fats in class. In this video, we're just going to introduce how esters are formed, reactions to make esters, and then reactions that esters undergo. Before we do that, though, remember we want to refresh our memory about the reactivity of carboxylic acid derivatives. In the last video, we talked about the most reactive carboxylic acid derivatives, which are acid chlorides and anhydrides. These can react with practically any nucleophile to give a large array of different functional groups and different products, right? But as the reactivity decreases, it makes sense that we need stronger nucleophiles, or we need more vigorous reaction conditions to induce these kinds of things to react. What we're also going to see is that it makes sense that these things are more reactive because they're higher in energy. And these things are less reactive because they're lower in energy. So while we can go from acid chlorides to esters, and we can go from acid chlorides to anhydrides, and we can go from anhydrides to esters, we can't go the opposite way. It's easy to go down in energy. It's hard to go up in energy, so that's what we're going to see in this video as well. So to start off with, how do you make an ester? Well, there's a couple different ways you can do it. There's a lot of different ways you can do it. One simple way is just to alkylate a carboxylic acid. Remember, esters are named as alkylated carboxylic acids. For example, if we take propanoic acid and we treat it with a base like sodium hydroxide, hydroxide is a strong enough base to completely deprotonate our carboxylic acid. Remember, carboxylic acids are acidic because of their resonance stabilized anion, right? So this is a much weaker base than hydroxide. But now we've turned it from a bad nucleophile into a good one, and then this can react in an SN2 reaction with methyl iodide, or any alkyl halide really, to give an ester, this one being methyl propanoate. So method number one, alkylation of carboxylic acids under basic conditions. Pretty rare. This doesn't happen very often. The most common reaction to make esters is called the Fischer Esterification. And in this reaction, what we do is we take a carboxylic acid, let's say we use butanoic acid, and an alcohol, usually used in a large excess, and an acid catalyst, usually sulfuric acid. And what we get is an ester. This hydrogen combines with this OH to give a molecule of water. This is an equilibrium, and so we can shift the equilibrium from the carboxylic acid to the ester by using methanol as a solvent in a large excess, which pushes the equilibrium in this direction. And then what we're going to see when we talk about reactions of esters is that you can take an ester with water and an acid and push the equilibrium back in this direction if you use water as a solvent. So just like other reactions that we've seen, if you use methanol as a solvent, we're going to push the equilibrium in this direction. If you use water as a solvent, we're going to push the equilibrium back towards the carboxylic acid. So what's the mechanism of the Fischer esterification? Think back to these equilibria that we talked about in the ketone and aldehyde chapter, right? We have methanol as a solvent, and we have sulfuric acid as our acid catalyst. So the first thing that's going to happen is sulfuric acid is going to protonate methanol, right? In order to make this carbon more electrophilic, under acidic conditions, what we're going to do is protonate that oxygen. So we get a positive charge here and an OH, and now methanol is a decent enough nucleophile to attack that carbon and break our carbon-oxygen double bond, which gets us to this tetrahedral intermediate, right? Keep track of your charges, right? We had a plus charge between these two guys. We had a plus charge here between these two guys. Now we have a plus charge. We're never going to lose that plus charge. But now what's going to happen is methanol, which is our solvent, and our universal proton acceptor, since it is our solvent, is going to take this guy. And we get here. Where we're going, though, is to an ester, right? We want to reform our carbon-oxygen double bond. We want to kick this guy out as water. We know water is a byproduct of the reaction, so we need to protonate this oxygen to move in that direction. That's going to come from protonated methanol. So one of the lone pairs on this oxygen can accept a proton from methanol. Now that is a good leaving group. Now when we reform our carbon-oxygen double bond and this guy leaves, what we have, something that looks like this, we have an ester that just needs to get the proton removed. So in the last step we have a proton transfer to methanol. That's what's always the solvent is always going to accept the proton in these reactions, and that gives us our ester product. Remember, every single one of these steps is a reversible equilibrium, and so we're going to actually go through the mechanism of hydrolysis of an ester to give a carboxylic acid, just like you can hydrolyze acetals to give aldehydes. If we can influence all of these steps by Le Chatelier's principle, as we're going to discuss later. Okay, this is an equilibrium. So one way to shift the equilibrium in this direction is to add methanol or whatever your alcohol is, ethanol, propanol, isopropanol, as your solvent, and you can also remove water as it's formed. That's going to shift the equilibrium towards the ester product in the Fischer esterification. Okay, another way to make an ester instead of using carboxylic acid, we know that you can use acid chlorides with alcohols to make esters. We talked about that in the last video. So what reactions of esters are we going to talk about? Well, one thing that you can do for an ester is just go back to the carboxylic acid. This reaction is called saponification, which literally means to make soap, and we're going to talk about this in more detail in class. A simple saponification reaction would be something like this. If we had methyl propanoate, we react it with sodium hydroxide, right? Now hydroxide is sufficiently nucleophilic that we don't need any additional push for it to attack as a nucleophile. Reformation of our double bond kicking out methoxide gives us a carboxylic acid, right? So what's the point of this H3O+? Well, the problem is sodium hydroxide is a strong base. The second that it sees the carboxylic acid, it's acting like a nucleophile here, but acts as a base to deprotonate our carboxylic acid. So we get our carboxylate anion out of step 1, which then becomes protonated in step 2. Remember, these carboxylate anions with long alkyl chains are soaps, so that's why this reaction is called saponification. This is a reaction that we did in the first semester lab that you may or may not remember. We can also hydrolyze esters under acidic conditions, and this is just the reverse of Fischer esterification. So we take an ester with an acid catalyst and water as a solvent. We shift the equilibrium back to the carboxylic acid and methanol. So quickly, the mechanism here is exactly the reverse of the mechanism that we did. And remember, right, if water is the solvent and we have an acid catalyst, then all protons are going to come from hydronium ion. We protonate the oxygen to activate it towards nucleophilic attack. Water is our nucleophile here. It's the solvent, it's present in a large excess, right? We get our tetrahedral intermediate, which has this positive formal charge on oxygen, and we're going to lose that formal charge by transferring the proton back to a water molecule. What we want to do is get rid of that O-methyl. That's at least the net result here is we're going back to carboxylic acid, right? So we're going to transfer a proton here. That's going to be transferred from a hydronium ion. Hopefully you're recognizing a recurring theme here. If you want to make it into a leaving group, you protonate it, right? Now that it's a good leaving group, we can reform our carbon-oxygen double bond, kick this guy out, and what do we get? Well, we get our protonated carboxylic acid, which can then lose a proton to a molecule of water to give our ultimate carboxylic acid. Notice every single step, every single intermediate here is identical to the Fischer esterification goes in this direction. Hydrolysis under acidic conditions of an ester goes in this direction. Okay, so we said that you can't make something that's more reactive than an ester from an ester directly, but you can make something that's less reactive. So amines can react with esters to make amides. Usually this requires a significant amount of heat. This reaction, if you have an ester, you can treat it with an amine like ammonia, for example. Ammonia is sufficiently nucleophilic that it can attack to give O-. Notice that we don't have an acid, a strong acid or a strong base. So the generation of positive charges is okay here. Ammonia can immediately accept that proton to give us a neutrally charged intermediate. And then reformation of our carbon-oxygen double bond and kicking out of methoxide gives us our amide product here. Metal hydrides are very useful, and these are very practically useful reactions, unlike some of the ones that we talked about in terms of acid chlorides. Esters are routinely reduced with lithium aluminum hydride to give primary alcohols. We talked about this before. Now it should make a little bit more sense, right? We have an H- from our aluminum reagent that's attacking that carbon-oxygen double bond to give us our tetrahedral intermediate, right? Reformation of our carbon-oxygen double bond gives an aldehyde, which can go on to get reduced to the primary alcohol. If we want to stop the reaction, usually we use a bulky aluminum hydride reagent, which is diisobutyl aluminum hydride, usually abbreviated dibol or diba. This just has one aluminum hydride and it's sterically bulky, so it can stop at the aldehyde stage. Grignard reagents, as we know, add twice to esters. The reason being that initially what happens, let's say we have ethyl magnesium bromide as our Grignard. We have a carbon-containing nucleophile, which is very nucleophilic. It can directly attack that ester. Right? Reformation of our carbon-oxygen double bond initially gives a ketone, and then the ketone can undergo a second addition of ethyl magnesium bromide, which is going to give this, which upon treatment with water gets protonated to give our alcohol. So notice that two equivalents of the Grignard reagent are added to our ester, and the O-methyl is gone in our product. We're already familiar with this reaction. Now we kind of understand better why it occurs. So to summarize, esters have a really rich chemistry, especially they're very useful, and nature has selected esters as very useful intermediates for a lot of biochemical reactions that we'll talk about a little bit in class. You need to know that esters can be formed by the reaction of acid chlorides and an alcohol. We've already talked about that. By alkylation of carboxylates, or most commonly by Fischer esterification, which is an equilibrium between an acid, an alcohol, and an acid catalyst. You should definitely know the mechanism of Fischer esterification and acid catalyzed hydrolysis. You should know the mechanism of basic hydrolysis of an ester, and know how esters react with amines, aluminum hydride reagents, both lithium aluminum hydride and dibol, as well as Grignard reagents.